So, good morning, everybody. I am Sophie Bozonnet. I am home right now, like most of you, I guess, but I usually work at Toulouse Biotechnology Institute, which hosts 3 platforms providing services for the IBISBA network. I will talk to you today about what we do at ICEO concerning screening of enzymes for industrial biotechnology. But first, I would like by starting to remind you why enzymes are such interesting molecules. They are basically very efficient catalysts characterized by their selectivity towards specific substrates. As they mostly originate from temperate environments, they show optimal performances in mild physico-chemical conditions. That is to say, low temperatures and moderate pH levels, which is a benefit when one wants to reduce energy consumption and chemical uses. Finally, they are also biodegradable, and in many cases they can be reused, which thus contributes to the sustainability of the process in which they are used. However, they also, because they are adapted to mild in vivo environments, just as I've said, they can suffer from reduced capacity to support high temperature or extreme pH, or presence of unconventional chemicals such as solvents. Moreover, they are highly specialized for their natural substrates, but they can show a limited activity on alternative related compounds. Despite these drawbacks here, enzymes are relevant for very, very many areas, such as medical research, food and feed industries, or bioenergy. More precisely, in the frame of industrial biotechnology, what do we want to find in an enzyme? Well, it is better if they possess special characteristics on top of those necessary in vivo. First of all, they need to be robust, that is to say they resist degradation, to be used as long time as possible in the dedicated process. Sometimes they also need to work on slightly modified substrate or in harsh conditions relating to pH or temperature. Therefore, it is important. There is a need to find ideal enzymes, but where do we find them? There are 2 sources of we can explore. So first is the microorganisms surrounding us in every type of natural environments. They are a considerable natural reservoir that can already produce interesting catalysts. But there is also the diversity we can create from known proteins using mutagenesis and directed evolution. The generated sequence space that we produce then is immense, and if we can benefit from high throughput screening or help from computational analysis, we are indeed in possibility to discover valuable new enzymes. At PICT-ICEO, we actually provide a full set of expertise and equipment to help users achieving such kind of goals, answering their specific needs. Our facility is dedicated to enzyme high throughput screening and functional characterization, and is managed by a team of scientists and engineers dedicated to enzyme discovery and evolution. We have automats for colony picking, microplate organization, and liquid handling. All these robots are at the core of our high throughput screening facility. It allows us to work with libraries of mutants in 96 or 384 well format plates. We recently acquired a droplet microfluidic installation allowing screening rates of millions of mutants per hour, while at the same time we can really drastically minimize the reagent volumes. And it can be very, very critical when working with very expensive substrates. Downstream, this equipment for diversity sorting, we possess several protein chromatography systems, which allow us to purify proteins of interest that can be characterized in depth, either with biophysical methods, such as nano DSF or circular dichroism, or also via analysis of the reaction products, because we have a large analytical facility composed of several HPLCs and GCs associated to a variety of detectors, so that we can adapt to a large range of molecules and as a consequence to many types of enzyme activities. In the end, we offer a range of services that go from counseling to enzyme characterization, including our core activities of directed evolution libraries constructions and high throughput screening assay developments and implementation. In the frame of eBizBA, ECO offers to selected projects subsidized access to the infrastructure during 1 month. During this time, users will benefit from expert training on all equipments necessary for their research and from assistance by ECO staff to design and run all enzyme engineering and characterization experiments. To illustrate our activities, I will briefly describe 2 projects to which ECO has strongly contributed. The first is the European project OptiBiocat, which focused on the development of novel enzymes for the sustainable and cost-effective production of compounds used in the cosmetic industry. ECO was involved in the engineering of a ferrolyl esterase. This family of hydrolytic enzymes is involved in lignocellulosic biomass deconstruction, but they can also display an innate ability to catalyze transesterification reactions, which means transferring different acceptor molecules onto ferulic acid. The newly feruloylated compound can then display enhanced antioxidant properties, for example. To favor this transferulylation reaction, it is often required for the enzymes to perform at rather high temperatures and in presence of solvents. Basically, in both cases, mainly because it increases the solubility of substrates and products. The aim of our participation in OptiBiocat was to improve the stability of Aspergillus niger feruloyl esterase A, both in the presence of solvents and at elevated temperatures. And to do that, we used a directed evolution approach. Using 2 new synthetic chromogenic substrates, the screening strategy was based on the primary screen, using first indolil ferulate, which allow us to discriminate on solid agar colonies exhibiting active esterase as they turn blue, as you can see on the picture here. Expression of the ferulyl esterase was done extracellularly by the yeast Yarovia lipolytica. After we've done this first screening, active mutants were then assayed after culture in liquid medium using another derivative of ferulic acid, the 4-nitrocatechol ferulate. The color is slightly different here. We are working with some reds now. Activity was measured from culture supernatants in standard conditions but also in the presence of solvent or after a controlled heat shock, so that we can discriminate the mutants that are behaving better in presence of these two different constraints. This methodology was applied to a library of about 10,000 random mutants generated by error-prone PCR. And it allowed us to select 12 mutants, showing increased performances. Actually, it was interesting to note that though they were selected on either one or the other property, solvent or temperature resistance, we could actually find some mutants displaying better performance for both criteria. We didn't stop there. We wanted to go further, and that's actually what also directed evolution allows us to do. So we decided to recombine the mutations found in these 12 variants, and we did that in two ways, either using a rational manner for some, but also using a random methodology, using the staggered extension process method. We generated a second round library that was screened again using the same principle as the first one. And at the end of this screening, we obtained actually a quadruple mutant showing a TM increase by 9 degrees compared to the wild type, and also a solvent-resistant mutant with 2 times more activity in presence of DMSO. So this is the first example of a random evolution strategy applied to an enzyme for a basic, for a classic industrial aim. I will also try to describe to you another project, which is called BioSurf. This project was aiming at identifying new strategies to produce biosurfactants using enzymes or microorganisms. In this project, we targeted an endoglycoceramidase, which is an enzyme that normally hydrolyzes the beta-glycosidic bonds of gangliosides. This family, a little bit like the ferrolyl before, has a natural ability to catalyze transglycosidation reactions, but with low yields. And they can be used to produce alkyl polyglycosides, which are surfactants of commercial interest. Therefore, in this project, to increase the yield of the product's form, we chose to engineer EGC2 from Rhodococcus to improve its ability to perform transglycosidation using a cellobiazyl moiety as the donor and simple aliphatic alcohols or derivatives as acceptors. We first looked for amino acids taking part to the binding substrates of GC2, and 4 key residues were chosen for site-saturated mutagenesis, meaning that 4 libraries were thus created and screened using 4 different potential acceptor substrates. This strategy, by looking at all these mutants and testing them on every single acceptors, led us to identify 1 mutant that displays significantly enhanced ability to catalyze transglycosylation, as you can see from this TLC here, where here I hope you can see the level of transglycosylated product obtained for the mutant and compared to the wild type using the same condition. Monitoring of the time-dependent progression of the reaction revealed indeed a marked increase for the mutant. It actually led to an almost 7-fold increase in transglycosylation yield compared to the equivalent reaction catalyzed by the wild type enzyme. So this is very brief examples of projects that we have run on the ECO platform, and I hope this presentation can help illustrate the services we propose to the BISBA community. If you have questions, I will be pleased to answer them here. Thank you very much.